All right, we're going to continue with optimization today. So I have a somewhat interesting problem here. So let's say you have this can that has to hold 1 liter, which is 1,000 cubic centimeters. So that's the volume of the container. It says find the dimensions of such a can with the smallest surface area. So here's the idea. You got this can, right? And we're just going to look at it as just a regular old cylinder, right? A right cylinder. And what we could do is we can make this thing really, really tall, right? Really narrow, so that it holds 1,000 cubic centimeters. So you can see here, as I adjust the shape of this, it's going to hold a constant volume, all right? But the height and the radius of the can are changing, and notice that the surface area is going to change. So I don't know how good you can see that. Right now we're at a surface area of about 720 square centimeters. So if I try and make this thing a little bit taller, you can see I'm still holding 1,000 cubic centimeters, but now my surface area has grown, hasn't it? So let me try and make it not so tall. So I make it a little shorter. Looks like my surface area is down to about 600 something, 500 something. And then I could kind of go to the other extreme where I make this can that's really flat and wide like this. But look at my surface area, it's grown, right? 1,300. So somewhere in here, looks like 500 something is our least amount of surface area, right? Understand the problem? Yeah. Now, the task that we have is to somehow come up with a function that we're going to optimize, right? To find either the highest or lowest point on. In this case, we want to find a minimum value because we're trying to minimize the surface area. So I've already come up with the function. We're going to have to do it ourselves, but I went ahead and came up with the function, and I guess that's too big here. See if I can get them together. There we go. So this is the actual surface area function, if you graph it. And what we're trying to do is find the lowest point on that graph. So once we have the function, the actual calculus part of it begins, and you take derivative and figure out where it's going down then up, and then we're there, right? I mean, that's the idea. So you can see the correct solution to this is right there. So we need to get to that, all right? That's our goal. So you understand the problem? Questions on it? All right. So we're going to start this off by just writing down what we want to do. Our goal here is to minimize the surface area. Of this can, right? And then let's draw a picture. We have our can, and we get to adjust the shape of that. The main thing is it has to hold 1 liter, 1,000 cubic centimeters, right? So this can has some radius. Let's call that R. I'll do a little r. It has some height, which we'll call h. And if we're trying to minimize the surface area, we need a formula for the surface area, don't we? We actually need to come up with an equation for surface area. Now I'm just going to write A equals, in A I mean surface area, all right? So what is the surface area of that can? Well, I'm sure there's a formula somewhere in a book, right? But let's try and do it without any formulas out of books. What's the area of the top of the can? What's the area of the top of that can? Pi r squared, right? And we have the bottom of the can also, right? So the bottom side, we have that. Pi r squared again. So we have 2 pi r squareds, right? Let's go ahead and write that down. 2 pi r squared plus the actual outside of the can, right? So to figure out what that is, what we could do is imagine, here's our can, right? Here's our can. We're trying to find the area on the outside. So imagine if we were to cut this can open and lay it out flat like this. Then it's a rectangle, and we need to find the area of that rectangle. Now let's just talk about what that would look like if we laid it out. Do we know this distance right here? That's the height of the can, isn't it? Okay, so that's this height. Now, do we know this distance? Two pi r. So the way you can get that is it's the actual circumference of this circle. Because when I cut this and lay it open, the distance from here to here is actually the same as the circumference around that circle. Right? Okay, so the distance across is going to be 2 pi r. That's our formula for circumference. Y'all comfortable with that? Okay. That's pretty cool, right? We can just do that little. Now, of course, you could look in somewhere in the back of a book or something, and you could find that, but we have it here. So the area of this will be 2 pi r times h. So 2 pi r h. There we go. So right now, this is what we have, right? And we're trying to find the smallest value that this area equation can spit out. But the problem with it, well, can you tell me what the problem is with it right now? Pardon? The 1,000 cubic centimeters will come into play. It's going to come into play, but why can't I do calculus on this right now? Why can't I do my take the derivative and all that stuff? What's that? All the things we've been looking at have been functions of a single variable. Single variable. Area right now depends on two things. You have to give me the radius and the height for me to be able to give you the area, right? I need to somehow get this equation down to a function of one variable. And that's where the volume is going to come into play. See, right now, we can adjust this radius and this height however we want, right? But nowhere in this are we accounting for the fact that it has to hold 1 liter. And that's where that part's going to come in. Understand? That's the constraint. Okay, so I just did that just the other day. Okay, so we have this. I'll just put a little note here. Not a function of a single variable yet, okay? Yet, but we're going to get there, all right? Now, if you wind up ever taking Calculus 3, you'll learn that you can do this. You can, because we study what are called functions of several variables. So we can handle finding the max and min of a function of 2 variables, but we're not there yet. I mean, that comes later. Okay, so to do this, we have to use something else in the problem. That was the information that the volume of this thing had to be 1,000 cubic centimeters. All right? Now, volume, by definition, the volume of a can is what? Well, again, we could look up the formula, right? It's pi r squared, that's the area of the top, times the height of the can. So it's almost like you're stacking a bunch of circles on top of one another. So it's pi r squared, this area, times the height. So that's our volume. So what I'm going to do here is I'm going to put pi r squared times h must be 1,000. Do y'all agree with that? Now, I'm not using 1. You know how I said 1 liter? Because I need my units to be in like some unit cubed. And when you write 1 liter, you need to understand that that's 1,000 cubic centimeters. Right? That's why I gave that to you in the word problem, just so there was no confusion. If you write 1 there, you could you need to at the end know what what your answer means. All right. Okay. Shall we go? Continue? This right here, I called it last time we met, I called this the constraint. Constraint equation. And the reason I call it constraint equation is somehow it is constraining how you are allowed to adjust R and H. Right? You're not just free to let R and H be whatever you want, right? It has to maintain the 1 liter. So this is somehow constraining our variables. Now, how am I going to use this, though? I can solve this equation, right, for either H or for R, right? It's my choice. And then take that answer and plug it back into my area equation. And when I do that, I will have eliminated one of the variables. So it's our choice. We can solve for R or H. I think H is easiest to solve for here because we won't have to do a square root, right? So if I just divide both sides by pi r squared, I get the H is equal to 1,000 over pi r squared, right? So now I'm going to take that and I'm going to plug that into the original area equation. So I'll put it over here. My area now is 2 pi r squared plus 2 pi r times h, but h is 1,000 over pi r squared. Agreed? Any questions? I can clean this up a little bit, right? I think I get some pi's to cancel here. I think one of those r's cancels. 2 times 1,000 is 2,000. So why don't we write it this way? A, but watch how I do this. I'm going to do a of r. That's kind of like me writing f of x. I'm kind of stressing the fact that a is now dependent on one thing only. You give me radius, I give you everything else. I give you the area. 2 pi r squared plus 2,000 over r. And this is the function that you know how I graphed something earlier? A little while ago I had a graph of something up here? That's what I graphed, okay? And we're going to try and find its lowest point. So the next thing we need to do is consider what our restrictions are for R. Like, is R on a closed interval? Is R allowed to be anything? Like, what are our restrictions? Can't be 0, right? Can't be negative, all right? Now, if R is 0, we don't have a can, right? Okay, so you can't have any volume, right? You can kind of see it from here, too. If R is 0, H is undefined, right? So R cannot be 0. So how about this? R has to be bigger than 0 and less than, well, how wide can this can be? Infinite, right? In other words, you could have a can that's a mile wide and like infinitesimally tall, and it'll hold 1 liter. Now, theoretically, right? Theoretically. So we cannot restrict it. And that means we're trying to find the minimum value of a function on an open interval. So we do not have a closed interval. We haven't done one with a closed interval yet, have we? I don't think we have. So I'll do one today. All right, you all ready to do the calculus part? We've got the function we're trying to get. This has a name also. Does anyone remember what I called this function? That one was a constraint equation. This is called it's probably in your notes from last time. This is called the objective function. Did I do that last time? Did I say that? It's called the objective function. It's the one we're trying to figure out some information about, all right? It's the whole objective of the entire problem. All right, here we go. What am I going to do? Take the derivative, right? Okay, so let's take the derivative. A prime of r. Let's see, this should be pretty clean. I got 2 pi is a constant, 2 comes out. So 4 pi r. You know, one thing that students start to like lose track of is like we're doing a derivative of a function and we're differentiating here with respect to r. We're not doing a related rate problem where we're differentiating with respect to time. Those are completely different concepts. And so that's the reason I don't have like a dr dt here, because I'm not trying to see how the rate which one variable changes with respect to the other. That's related rates. If one thing changes, how does the other one change? This is just, hey, here's a function. Give me find the lowest point. So I just need to figure out where the tangent line is 0, right? Or possibly a cusp or a corner or something like that. All right, there's the first part. How about the next part? Negative 2,000 over r squared. So I'm really hoping that you can take the derivative of this without too much work. Just thinking that's r to the negative 1 when you bring it up, and then do your power rule, right? So that's this. And now we want to know when that's 0. So when is a prime equal to 0? That's one question. And then when does a prime not exist? So what about when it's equal to 0? We have to set that to 0, don't we? Okay. And I hope, again, that you've done this enough that you know pretty much right away you're going to need a common denominator. Can't seem to kick this cough. Yeah, no. That's r cubed. Okay, so I had to multiply top and bottom of this one by r squared. Yeah. Put them together. So all I have to do is set the top to 0. And the next thing would be to try and solve for r, right? So move 2,000 over, divide by 4 pi. So r cubed equals, I believe that's 500 over pi. Y'all agree? And then we take the cube root. So r is equal to the cube root of 500 over pi. Now I hear some punching away on the calculator there. That's good. Yay or nay? You get something? Oh man, I don't have my calculator. Wait. Oh, I do. You got what? 5.41? Yes, that's right. Okay, so if this is about 5.41. I'm going to put centimeters because we're measuring the length of the radius. So we've got about 5 centimeters or so. And then, where does the derivative not exist? At 0. But 0 is not in our domain. So we don't need to consider it. All right? So nothing here. So at this point, you're not done. All right? And I think I told you this last time. You will lose points on the final, or on anything I give you, if at this point you box this up and say, okay, that's where we have a minimum. Because you haven't shown anything about a minimum yet. All you've shown is that there's a critical number, that the derivative is 0 here. It could be a maximum, though. It's not, though, but you know. Okay, so now what we do is we put 5.41 on a number line, and we pick 2 test points, and we're going to test those points into the derivative to see if our function is going up or down. So I'm going to put 2 here, and how about 10 here? That work for you? I can't plug in 0, because 0 is not in our domain. Okay, so 2 is going to go into the derivative. And I actually like this version of the derivative right here, that one. That's a nice one to plug into. I mean, you could do it here also, but 2 into here. The reason I like it here is because the bottom's always positive, so I don't really care about that. So if I plug in 2 here, I get 8. And 8 times 4 is like 30 something, and then times pi is like not even 100, right? And then you take away 2,000, so it's negative. So that means our function is going down here. The area function is decreasing over here, right? And then if I plug in 10 cubed times 4 pi, we're going to get a huge number. it's going to be positive, so the area function is going up here. So I have now shown that this is where we have a minimum, right? Okay. So now what I say is we have a minimum value, and this is the only minimum, right? There's no other minimums out there, or else our function would have to do that again somewhere. But it doesn't. It only goes down then up, and that's it. So we have a minimum surface area at r equals cube root of 500 over pi, which is approximately 5.41 centimeters. Now, I have not answered the question. The question was, I believe, if I remember correctly, what are the dimensions of the can that give you the minimum surface area? So I've only found the radius. So the next thing to do would be to find the height, right? So do we have any way of getting the height? Yep. We actually had it. It was our objective equation. I mean, not objective. It was the constraint equation, wasn't it? Our constraint equation, we solved that for h. And that's normally what will happen in these, is you'll have to go back to the constraint equation to get one of the other variables. So using the fact that h was equal to, I think it was 1,000 over pi r squared, right? We have that h will be equal to 1,000 over pi times, let's just do the 5.41. Is that okay? Square? Square. And see what you get. While you're doing that, I'm going to do something else while you're doing that. No, I think you may need to put this in parentheses when you divide. I think you divided by pi, but then multiplied by that. What do you get? 10.87. Sounds about right. Sounds about right. While you convince yourself that that's true, I'm going to write something down here. It's kind of interesting. Okay, so what I've done here is I've rewritten this, what h is, but instead of putting r squared, instead of putting pi r squared with a decimal, remember r was this, right? And this really means cube root of 500 over cube root of pi. And remember that cube root really means raising it to the 1/3, right? Yeah. So I took the 500 and I raised it to the 1/3, but then I squared it so it becomes 2/3. Then I took the pi that's on the bottom and it was cube root, but then I squared it. So do y'all see all this? Yeah. Y'all see where that comes from? Okay, so watch what I'm going to do. First, let me take care of this. That's pi to the first power over pi to the 2/3 power, isn't it? And that leaves you pi to the 1/3. Agreed? On the bottom? Okay. So I have a pi to the 1/3 on the bottom. Now, what about this 500 to the first power over 500 to the 2/3 power? Subtract the exponents. 1 minus 2/3 is 1/3 again. So isn't that 500 to the 1/3? And then isn't there a 2 sitting out in front of all that? Yes? So this is 2 times, and then if I put these back together, isn't that this? This is just, I'm just messing with algebra here. So if you follow this, hopefully you do. But yes? Okay, isn't this twice the answer? Isn't that twice the radius? See, the radius is this, right? Isn't the height just twice that? That's what this is saying to us. Maybe you notice it here. 10.87 is about twice this. It's about, but there's decimal, there's some error because of decimal. But the true exact answer, if you take the exact answer and you plug it in, and you do some algebra on the exponents, you'll see that the optimum solution is to have your height be exactly twice the radius. See that? Twice the radius. What does that mean? Oops, did I do that? What does that mean? What we're getting here is that the height has to be twice the radius, right? That's what we're getting? But what's 2 times the radius? The diameter. So isn't this saying that the height needs to be equal to the diameter? Yeah. This is saying that the height needs to be equal to the diameter. So if I build a can, and I want to have the least amount of surface area, I want the height of the can to be equal to the diameter of the can. And that will give me the minimum surface area. It's interesting. Now, if you go back to like the 1950s, 60s, the first thing that comes to mind is like oil cans. Like you used to go buy oil for your cars, and they came in cans, and you would just like have this thing that would punch a hole in the top. You put the oil in your car. Yeah, like a little spout. It wasn't these little plastic bottles. So if you go back and look at those cans, a lot of them have the dimension where it's like diameter equals height. And that's because in the beginning, they used that optimum solution to build a lot of things. Now, you take a look at like a soda can, right? Your soda can is definitely not diameter equals height, right? And there's probably a couple of reasons for that. One of them is, it would be weird in your hand. But I guarantee that there is an optimum solution used in the development of a can, because soda cans are not the same type of cylinder that we have here, right? They have like this little bulb on the bottom, right?
They have the reaming to make it stronger.
It's stronger in certain areas, right? You have the cap on top, so it's not a perfect cylinder. That little like indentation on the bottom, right? That's so if the soda heats up in a car, that bottom will pop out instead of blowing up. So I mean, there's all these different things that are taken into account. So, but they do it the exact same way. It's just their function is not this simple. They have their area function is more complicated. It's like they have weighted different, it's like maybe, this shape down there, right, is more like a bulb in there, and then maybe that in there is a different density of aluminum, so the cost of that piece is going to be a little bit more. And they have to take all that into account, right? But this is the same idea though, right? So kind of interesting. Did we finish? Yes. So I think the best answer to this would be, that your radius has to be equal, your height has to be equal to your diameter. And then you could give the actual values. Does that seem real world enough to you? I mean, if you're manufacturing 1 million cans a year, right? And you can somehow save yourself, 1 million doesn't even seem like enough, right? You think Coca-Cola company makes more than 1 million cans a year?
Let's say a 400 million production run of a single product.
Probably, and maybe you can save yourself, 3 cents a can if you optimize your solution. It can start to add up, right? All right. I'm sure they do it the same way with plastic. All right, let's look at another problem here. This is going to be a little bit different. So there it is. Find the point on the graph of y squared equals 4x minus 1, which is closest to the point 3, 1. This is a very different problem. So you've got this parabola. I'll bring it back up here in a second. But, yeah, that should be good. So I've got this y squared equals 4x minus 1 as a parabola. It actually opens sideways because it's y squared, not x squared. So we've got this sideways opening parabola. And then we have this fixed point. This is the point 3, 1. And what we're trying to find is which point on this graph is closest to 3, 1. See, it's not straight up, right? That point right there, straight up, is not the closest point. It's not straight over, right? It's somewhere in here. Somewhere in here is the closest point. Obviously down there, no, right? But somewhere between about, here and here, we have a closest point. So this doesn't seem very real world until you start to think about this as being like a planet, and maybe this is some sort of asteroid, and it's got some sort of path, right? Right. So this is how we determine like how close something is going to come to Earth, right? You heard like it was a near miss, right? It was like 2 million miles away or something like that. This is how they can figure out how close it's actually going to be, and determine later on like when it's going to happen.
And how to calculate trajectories for satellites passing planets.
Same thing. Yep. So can we find the minimum distance, right? Minimum distance between these 2 points? Everyone understand the problem? All right. So I'm going to have you help guide me a little bit more on this one to see if y'all are really starting to get this or not. So I'm just jot this information down so I can bring up another screen. By the way, the optimum solution is right there. Okay, so we will find that. All right, what do you got? What's our goal? What did I say in the last problem? What was our goal? Okay, so what do you want to do here?
We want to see the
Minimize the distance. Let's write it down. Minimize the distance between y squared equals 4x minus 1 and the point 3, 1. Okay. Right? Minimize the distance. Last problem, we wanted to minimize the surface area, right? So what now? We need to find an equation, right, which will become a function eventually, right? The equation we get might be an equation with 2 variables. We don't know yet. But we need to find out some equation that gives us the distance, right, between these two. Right? Okay, so let me draw this picture again. I've got this parabola. And if you didn't know that that parabola looked like that, because if this came out of it like a word problem out of the book, they're not going to give you the graph. So if I were trying to graph this, what I would do is I'd make a little t-table, and I would just plug in some points and just plot it. I would have to know it's a parabola, okay? And then once I get enough points, I could draw it, all right? All right, so the point that we're looking for lives somewhere on this parabola, right? We don't know where yet. So how about I just label some arbitrary point? And it has some x coordinate and some y coordinate. Agreed? Now this point here is fixed, 3, 1. The distance between these two, this line, we can get. What is the distance between 2 points? There's a formula for it. So I'll remind you how to get it. See, I'm not a big fan of memorization. I've always believed that understanding is better than memorizing. So if we ever had 2 points sitting here, call this x1, y1, x2, y2, then to find the distance between them, all you have to do is construct a right triangle. And remember that this is the difference of your x coordinates. This is the difference of your y coordinates. Right? That's your difference of x's. This is your difference of y's. And then using a Pythagorean equation, you get a squared plus b squared is c squared. Right? So if we call this distance, then this squared plus this squared should equal this squared. So distance squared should be equal to x2 minus x1 squared plus y2 minus y1 squared. And then if you take the square root on both sides, we get the distance formula. So if you remember the distance formula, if you do, it's the square root of this. Yep. But that's where you can get it from. See what I mean? Like if you understand it, you never have to really care about memorizing because you can always generate it yourself. All right, so let's go ahead and write this down. The distance is equal to the square root of, now these are our points, right? I'm not going to use x1, y1, x2, y2. These are our points. So why don't we do the difference of the x coordinates? What's the difference of the x coordinates? You can do x minus 3 and then squared. Could I do 3 minus x squared? It turns out that it's okay because you're squaring it. So x minus 3 squared is the same as 3 minus x squared. You take away the squared, it's not the same. So it's okay if you switch the order. But I'm going to do this x minus this x, and then I'm going to do this y minus this y. So plus y minus 1 squared. Are we good? That is an equation that gives me the distance between these 2 points, but there is a problem with that equation. What's the problem? It has 2 variables. So we need to get it down to 1. Anybody have an idea of how I can get that down to 1? The what?
The original function.
How do you mean? I'm not disagreeing, but how do you mean?
Y squared equals 4x minus 1 set that equals 1.
This right here,
X, yeah.
that is a constraint, isn't it?
Yeah.
See, look, the way I drew this picture, this point xy actually lives anywhere, right? What puts it on the parabola? What puts it on this parabola? If I use this equation, right? So I can now use this as my constraint. So this is going to become my constraint equation. And that means I can solve it for either x or y. What would you prefer to solve that for? Yeah, if you solve for y, you're going to have to take a square root, right? Okay. If you solve for x, you won't need to. So how about we solve it for x and then come to this equation and replace that x with whatever it turns out to be. And yes? Yeah. Okay. So my constraint, let me solve it for x. So I'm going to add 1 to both sides and then divide by 4. So y squared plus 1 over 4 equals x. I'm probably going to wind up doing like 1/4 y squared plus 1/4. I don't know yet, but this is what it is, yes? So now back over here. Distance equals square root, and then x, which is this, y squared plus 1 over 4, minus 3, that squared, plus y minus 1 squared. That's pretty ugly, huh? Do you agree that this is now a function of a single variable? In fact, I probably should have wrote d of y instead, and I think I'm going to do that. I'm going to write d of y. That way, everyone is aware of the fact that I have now reduced this equation with 2 variables into a function of a single variable, and then I can do calculus. What do I need to consider next before I move on? Domain. So are there any restrictions on y? Now, y is the y coordinate of this point. So on this little parabola, is there any restriction on y? Why can't it be negative? I mean, could I have a point down here?
Yeah.
It could be negative, right? But does it make sense? I mean, we looked at the picture, didn't we?
Yeah.
And in terms of the picture, we know that a point down here is not going to be the answer. Do y'all agree? So technically speaking, there are no restrictions on y. But because we have looked at the picture, I think we can convince ourselves Or maybe we can lock our y into a closed interval. Do y'all want to try and lock y into a closed interval just by the picture? Y coordinates. If we were here, wouldn't y be 0? We know that's not the answer, right? Agreed? And then would you agree maybe way up here, like, I don't know, y is 6? Right? We're looking at the y coordinate. So if y is 6, I think we can be safe to say that our answer is somewhere before that. And if y is 0, I think you know what I'm saying? Like between here and here. Our true answer is in there. Yeah? Okay, so I'm going to go and lock this in, and I'm going to look at this on the closed interval 0, 6, and just remember I'm talking about y here, okay? Because the variable is y. If you want, you could write this. Okay, either one.
Did you choose any distance? Like, if I look at the graph, should it always
Did
be?
you do like 1 and
Would it be better if you to choose a y distance to get a better calculation than to actually try to hone in on it based on a graph?
I'm not sure what you mean.
Reducing the amount of distance between 0 and 6 to, like, say, 4 and 1.
Oh, you mean get a better interval?
Yeah, just to reduce it. I mean, just.
You can, but do you remember how we do the closed interval method? We take the derivative, right? And we find the critical points, right? So we set it to 0 and then where it doesn't exist. And then we don't do a number line and test points. We just plug those answers into the original function and then the two endpoints. So if you were to have gotten two closer endpoints, doesn't matter, you still have to plug those in, right? You still have to evaluate that function at two different points. So I'm not sure it really, I would say be really safe and pick y's that are so far apart you know your answer's in there, right?
That was my question.
Yeah. Okay. Good? We need a derivative. And I think that's probably the ugliest part of the problem. So I'm going to rewrite d up here before I take a derivative. And I'm going to write 1/4 y squared. I told you I felt like I was going to come back to this. Okay, all I did was divided those. I can put the 1/4 and the -3 together, right? But I'm not even going to do that right now. Is that all right? I need to take the derivative of this. Yeah? Okay. All right, it is what it is. It is what it is. My favorite is, I think it's Such is Life, or yeah, Such is Life. Such is Life. Famous words of an ex-girlfriend of mine. Famous last words. I mean last words like our parting words. Her parting words to me, such is life. See you later. All right. Here we go. Derivative of the root of something is 1/2 times the root of all that, right? Okay, so watch what I'm going to do here. 1/2 times the root of all that junk, right? And I use junk as a technical term here. I remember my professor doing that many times, all right? I just don't feel like rewriting all of that. And as we're going to see, it's not even going to matter at the end of the day, all right? We'll see, though. All right, so that's the derivative of the root of something, right? It's 1/2 times the root of that stuff. Okay, times, now we do chain rule. We have to go inside and start taking the derivative. I have an addition right there, don't I? So I can do these separately. So I can do this and this separately, but I will need a set of parentheses. So let's do the derivative of this one first. It's chain rule. 2 pops out, right? So we've got 2 in front of 1/4 y squared plus 1/4 minus 1/3, all of that to the first power, right? Because the 2 came out. times the derivative of its inside, which is just 2 comes out. So 1/2. 1/2 y? 0, 0. So just 1/2 y? Agreed? Okay. Now here comes my plus sign. That's this piece. And then the derivative of y minus 1 squared. So the 2 again pops out, times y minus 1, times the derivative of what's inside. Derivative of y with respect to y is 1, and derivative of -1 is 0. So there's a 1 out here. I don't need to write it. It's not so bad. It looks bad, but it's not so bad. We good? Let me clean this up a little bit. Check out this 1/2. This 1/2 out here has to multiply times this, and that 2's out there. So they're going to go away. And then just the y can go through. So I've got, on the bottom, 2 over root junk. On the top, 1/4 y squared. Let's go ahead and put these together. Well, I'll put them together in a second. Plus 1/4 minus 3. Okay, so that's this. Oh, wait, hold on. I should make that y cubed. Y cubed, and then I should, I guess I'm going to have to put those together. What's 1/4 minus 3? So 1/4, take away 3 over 1, common denominator, 1/4 minus 12 over 4. So -11/4. -11/4 y, right? Because I have to pass that y through. So that y went here and to those. And then I still have over here 2y minus 2. Good? Okay, there's my derivative. Can I pull 2? Well, yeah, I don't have 2's here. Let me just leave it for now, and then we're going to try and figure out what we're going to do with this. Oh, we can combine those too. Oh, crap. Yeah, we can combine the y's. These y's we can put together. So we need to get a common denominator here. So this is like 8 over 4. So this is minus 11 over 4 plus 8 over 4 is minus 3 over 4. So 1/4 y cubed minus 3/4 y minus 2 over 2 times the root of the junk. So when is the derivative 0? D prime equals 0. And then when does D prime not exist? All right, here we go. So we have 1/4 y cubed minus 3/4 y minus 2 equals 0. Right? Y'all agree? Uh-oh. That's not a quadratic. That is a cubic equation. Why don't we clear the fractions? Let's get rid of the fractions. I'm going to multiply everything by 4. Y cubed minus 3y minus 8 equals 0. Just multiplied everything by 4. Just looks a little nicer that way. How do you solve this equation? Well, it's not quadratic, right? So there was something in college algebra. Maybe you remember this. The what? Rational zero test, where you do that synthetic division and you try and. Do y'all remember that?
Yeah, try to pull the factors out of it.
You look at like the number in the front and the back, and you make this list of numbers, and you try synthetic division on it.
Put a placeholder in there.
Yeah, you have to place a 0 in there. Do y'all remember that? I mean, if you don't, it's okay, because it's not going to work. And the reason it's not going to work is because this that method works if your answer is a rational number, which means your answer is a fraction. And this turns out to be an irrational number. The answer is an irrational number. I think it is. But so how can we solve an equation if everything we've learned has failed? Or we don't have a technique. Anyone have a guess as to how you do it? You've done it. Newton's method. That's how you do this problem. You would do Newton's method on this. Do we have a good guess as to what we think the answer might be?
I like 2.
Y is maybe 2, right? Somewhere around here, and then we could apply Newton's method, couldn't we? Well, I'm going to save us some time. Let me erase a bunch of stuff. Do y'all understand where we are, though, with the problem?
Yeah.
I mean, we are at a point, and of course, I would never give you a problem like this on a test that you're sitting there in class where you now have to do Newton's method. The point of this is to show you how we can bring a lot of different ideas together to answer something, right? But I guess the what's on the table in terms of what's in your toolbox of how you do things, it includes Newton's method now, which really means a computer, right? So I'm going to go back up to the section on Newton's method here. Oh, wait, I did it out of order, so it's after this. There it was. Remember that little thing I had up there? And I'm going to do everything in terms of x, not y. So I'm just going to rewrite this equation, y cubed minus 3, y minus 8. I'm going to do x cubed minus 3x minus 8. So x cubed minus 3x minus 8. And what was our guess going to be? I think we had said 2. Let's try 2 and see how fast it gets there. I only did 5 iterations, so let me just be safe and do 8 iterations. I think we're there. Let me erase this. Looks like about 2.492.
Now you're down there.
And I'm way out, right? I think we've got a pretty accurate answer here. 2.49? Yeah, let's go 2.492, all right? So now I know that d prime equals 0 at y equals 2.492, approximately, yes? All right, now we still need to look at where the derivative didn't exist. The derivative, whoa, I don't know what happened there, does not exist. And that would happen when the junk was equal to 0, or if the junk was less than or equal to 0. Right now, where am I getting that from? Why am I doing that? The derivative had the root of the junk down there, didn't it? Remember that? The derivative had all that stuff over 2 times root junk. If that junk is negative or 0, I get division by 0, I get root of a negative number. But what does that quantity right here represent in our picture?
The original function.
Isn't that the original function?
The distance function.
It's the distance between those 2 points, right? Can it ever be 0?
No.
Can't ever be negative either. So without doing any real analysis, like actually trying to figure out like a domain or anything, if we understand that this is the distance between our parabola and our point, right? This is d, and that is what that is, right? That can't be 0, and it can't be negative, right?
Yeah.
So this is not going to happen. But it's truly from the framework of the original problem that I can do that. Had someone just thrown this on the board and never told me where it came from, I would actually have to algebraically try and figure out like what the domain restrictions were. But you could do it, and you can mess with the inside, and you would see that it's a quadratic under there. And you would set it equal to 0, and you would find complex solutions. In other words, square roots of negative numbers when you try and use quadratic formula. So that would tell you, hey, it's never negative, or it's never 0. So that means it's always positive or negative, and it would always be positive. Is that
Yes, yes.
Okay.
Distances are
All right. We are going to move on. All right. Next thing. What now?
Number line.
Number line. Number line. Oh, wait, hold on. We did closed interval. Oh, we did closed interval. Now, could you have done number line? You all right? Could you have done number line? Yes. Had you said, look, y is on an open interval, you could do number line test points and you would get it the same way. But I wanted to do at least one with a closed interval. So we are on a closed interval. So what we're going to do is we're going to calculate d, right, d at 2.492. We're going to calculate d at, what, 0? And d at 6. And remember, d is the y, right? Sorry, d is the y. We're plugging it in for y into the distance function. And the distance function, they all had that root. And I have since erased it, but I think it was root, it was 1/4 y squared minus a fourth, plus a fourth minus 3 squared, and then y minus 1, right? So that was our original distance function. So we've got to plug 2.492 into it, plug in 0, and plug in 6. Right? Now, I'm not going to, because it's going to take too long. So I'm going to see if the computer, I think I have it on the computer here. I can't go out to 6. I only allowed my... Okay, well, I can just throw it into my code real quick. Let me see. Okay, so if you plug in 6, so if you plug in 6, the distance you get here will be 8.004. Okay? That all right? If you plug in 0, oh shoot, hit the wrong thing. Stop it. Okay, if you plug in 0, looks like you get 2.926. And then if you plug in the actual 2.492, if you plug that in, you should get something like the decimal 1.913. And remember, with the closed interval method, the biggest one is your max and the smallest one is your min. And so this is our minimum. So the original question was asking us what? I forgot. Find the point on the graph which is closest. So we have not answered the question. We have found the minimum distance, haven't we? We have found the minimum distance, but we haven't found the actual point. And we do know the y-coordinate, don't we? So how do we get the x? Well, go back to your constraint. And your constraint had x equals 1/4 minus something like that, right? X is, yeah, x equals y squared plus 1 over 4. Oh, okay. So if you just plug in 2.492 into here, square it, add 1, divide by 4, that'll be your x-coordinate. I'm curious to know, 2.492 squared plus 1 divided by 4. 1.80 something. So that is our point. Does it look right?
Yep.
I mean, from the graph.